This demonstration immediately follows up my lecture on resonance. I still have a portion of that lecture here on the board. Here on the board, taking damping into account, we have what is called a forced DHO. So for the damped harmonic oscillator, it has its own natural frequency, omega naught, and then recall that omega is the frequency of the driving force. If ultimately the driving force frequency matches up pretty closely with the natural frequency of the oscillator, then from this graph, large amplitude oscillations occur. You end up with a finite sized resonant peak. So I demonstrated this originally by using a pendulum. I'm going to follow up with another type of pendulum apparatus here as well in this demonstration. That's this apparatus right here. Okay, now it may not look like much, but this apparatus right here is actually a very primitive distant ancestor of modern communications devices such as cell phones. What I'm going to do is I'm going to use this device to send a message. I'm going to send a message from one side of the device to the other. Here's how I go about doing so. I have here three pendulums. Recall that the natural frequency of a pendulum depends upon its length. The natural frequency is the square root of G over L. One of these pendulums, this one here, I'm going to think of as my transmitter. It's going to begin to oscillate when I set it into oscillation with a frequency that's equal to its natural frequency. Now, all three of these pendulums are attached to this metal cylinder. This metal cylinder, by the way, is resting on two nails. There's a nail here, and there's a nail here. So when this pendulum here begins to oscillate, it then causes the entire cylinder to begin to oscillate. And then the oscillating cylinder acts as a driving force on the other pendulums. Which of the other pendulums is going to resonate? Obviously this one here, which has the same length as this one here. In other words, the natural frequency of this receiver pendulum matches up exactly with the driving frequency of this twisting cylinder, which is the same thing as the natural frequency of this original transmitter pendulum, like so. This pendulum here, which is of obviously different length, will not resonate because its natural frequency does not match up with the other two. And then what I can do ahead of time is I can set up a code of some sort. So for example, I can say that a specific amplitude of oscillation corresponds to a piece of information, such as a letter of text. Let's just say the letter A. So now what I'm going to do is I'm going to send the letter A from my transmitter pendulum here to my receiver pendulum here. Now, in order for this to occur, I do in fact need to get these pendulums as still as possible, and these two pendulums here have to have the exact same length. And now let me go ahead and set this into oscillation like so. Okay, notice that the cylinder is beginning to twist at the same frequency. And now notice my receiver pendulum on my left-hand side is in fact beginning to resonate. In fact, if you give this a moment like so, notice that the two pendulums are now in phase with each other and they are oscillating with the exact same amplitude. So what I've done here is I've sent, for example, say the letter A from my transmitter pendulum over here on my right to my receiver pendulum over here on my left. Okay, now there are a lot of disadvantages to sending information mechanically as I'm doing here. For example, there's a lot of damping that occurs here. Almost immediately, the energy is lost as heat. If you give this situation enough time, eventually all of the pendulums will just end up at rest. In addition to that, the speed of the transmission of the information is extremely small. It took like 20 or 30 seconds, for example, for the information to go from one side of the apparatus to the other, even though the two pendulums are only separated by a few inches. So instead of doing all this mechanically, we instead do it electronically. Here's an idea as to how you would do this electronically. Don't think of it, for example, in terms of cell phones. An easier way of picturing it is in terms of, say, walkie-talkies. So let's say that you speak into one walkie-talkie, and when you do, your voice has a frequency. Then, by means of the microphone, what happens then internally in that walkie-talkie is that the frequency of the sound wave associated with your voice is turned into the frequency of an alternating electrical current within that walkie-talkie. That alternating electrical current, however, transmits radio waves of the exact same frequency as that of the alternating current, as that of your original voice. The radio waves then are broadcast outwards. Think of the radio waves as being analogous to this twisting cylinder, because then those radio waves strike the other walkie-talkie. And when they do, they then cause an alternating current of the exact same frequency as that of the radio waves inside of that second walkie-talkie. And then the process of going electronically now from the electrical current to the sound wave of the voice coming out of that walkie-talkie is a reverse of what happened in the original walkie-talkie when you spoke into it. So suffice it to say, you then have a sound wave coming out of the second walkie-talkie that has the exact same frequency as the frequency of the sound wave from the original transmitting walkie-talkie when the person spoke into it. So this right here is a very primitive example of a communications device. What this means is that all of our modern communications, at least in part, is based upon the physical principle of resonance.